fellow mathematicians. Welcome to the podcast where mathematics is figure-outable. I'm Pam.
And I'm Kim.
And we're here to suggest that mathematizing is not about mimicking or rote memorizing, but it's about thinking and reasoning, about creating and using mental relationships. That math class can be less like it has been for so many of us and more like mathematicians working together. We answer the question, if not algorithms, then what?
In today's episode, ratio tables. I'm so excited, Pam.
Raise the roof.
It is our favorite tool for solving multiplication and division problems and our favorite model for building proportional reasoning and solving proportions.
We love ratio tables. Give us a high five and a happy clap for ratio tables. Totally love them as tools. So let's be clear. What is a ratio table? If you're like me and Kim, we never saw ratio tables as students, especially as tools for solving problems. They just didn't even exist. I dealt with a lot of problems in high school to do functions and functional relationships and all that. But what is a ratio table and why might we be interested in using it to mathematize multiplication and division problems? So a ratio table is a paired number table, but it's a special paired number table where all of the ratios are equivalent, where all of the entries form ratios, and those ratios are equivalent. So what does that mean in layman's terms? For example, if I had, say, the scenario where I had 27 sticks of gum in a pack. We like gum, we chew gum. You can picture a pack of gum. It has 27 sticks, random kind of in that pack. Then I have 27 sticks of gum in a pack. I might have a table that says 1 pack to 27 sticks is equivalent to 2 packs would have double that, 54 sticks of gum. And all of those succeeding ratios, like I might have 10 packs, would have 270 sticks of gum. So it's the ratio of 1 to 27, 2 to 54, 10 to 270, could be 20 to 540. Like all of those ratios are equivalent. And if those ratios are equivalent, then that is a special paired number table that we call a ratio table. So you might find it interesting that a mathematician who works with illustrative math, Bill McCollum, wrote a fine blog post the other day called "Ratio Tables Are Not Elementary," which might lead you to believe that maybe we shouldn't use them in elementary school. However, we would actually agree with him that the way he describes a particular use of tables in grades 3 would go away and isn't particularly helpful for much. We would agree with him in there. However, we conceive of ratio tables in the realm of multiplicative reasoning quite differently than just a list of, say, single-digit facts. So that could be a ratio table. I could have something that looks like 1 to 7, 2 to 14, 3 to 21, 4 to 28, and it could kind of be a list of what some people call multiplication tables. And that would be like the table for sevens. That's a kind of limited use of ratio tables. But we offer an alternative view of how ratio tables can be used in developing and using multiplicative reasoning. I posit that ratio tables can be used first as organizers of information to model, represent a scenario or a situation. So if we have a situation like the pack and sticks of gum that we could literally say, hey, let's sort of organize this information. We could kind of put it in this table and it would represent that pack to those sticks and different numbers of packs to sticks that always represented 1 pack to 27 sticks. In other words, anywhere in that table, every one of those packs had 27 sticks in it. That makes it a ratio table, and we can sort of organize information. That's kind of the first way. But secondly, we can also use ratio tables as tools to represent strategies for multiplication and division. So as we develop alternative strategies with students, and students are using relationships and connections to multiply and divide, we as teachers can come in and represent their thinking using ratio tables. Now, we can also represent their thinking using open arrays, the area model. We can also use equations But one of the tools that is so powerful to represent their strategies, those relationships they're using for multiplication and division, is a ratio table. That is another way that we can represent the way they're thinking about solving multiplication and division problems. Third, ratio tables can be used as actual tools for solving multiplication and division problems. Like they actually become the way that I begin to think multiplicatively to solve multiplication and division problems. They're actually tools to solve. So let me just say that again. One, they're kind of organizers of information. They sort of model the situation. They represent what's happening. And then we want to kind of move students. We want to help them transition to modeling their strategies, representing what they do, the relationships they use to solve problems. And then lastly, we want to transition students to actually use the ratio table as a tool to help them keep track of the relationships they're using, and they actually use it to help them solve multiplication and division problems. Now, we then could go to middle school and continue to have that go, and then use that ratio table as the proportional tool that it is to solve proportions using proportional reasoning. But today we kind of want to talk about how ratio tables could be used in these multiplication and division situations, these multiplicative reasoning situations. Because as students begin to use ratio tables, they learn to scale in tandem. As I double the packs of gum, I double the sticks of gum that I have. As I multiply the packs of gum times 10, I multiply the number of sticks of gum times 10. That I'm sort of scaling in tandem. And that active scaling in tandem is leading toward this thing that they'll do when they are solving proportions with non-unit rates.
Right. So, okay, you just said a lot of really important things. And it's so funny because
going.
It's actually a conversation that via text just had with one of my son's teachers, and said, this is my favorite model for multiplicative relationships. And so let's break down some of what you just said. First of all, unit and non-unit rates. As a 3-5 teacher, that's something that we deal with all the time. Unit rate multiplication problems. Yep. So let me give you an example. If we are talking about apples in a bag, we could have 3 apples in one bag, and the question could be how many apples in 4 bags. So
that's a typical multiplication question you'd run into in 3rd grade.
Sure. And so we could have students who skip count, like you just mentioned, skip count up per bag. And that would look like 1 bag on your ratio table, 1 bag for 3 apples. And they could say 2 bags would be 6 apples, 3 bags, 4 bags up the ratio table. But we could also have students use that as a tool to represent their thinking. And they could have 1 bag for 3 apples, or 3 apples for 1 bag. And then they could think about doubling and go double the number of bags would be double the number of apples. So that on their ratio table, it would say 2 bags and 6 apples. And then if we're trying to figure out how many for 4 bags, then they could double again and say, now I have 4 bags, and double the number of apples would be 12 apples.
In other words, they're not listing them all, right? Like you could list them all, but then we want to encourage students to think in bigger chunks of numbers. And so they could go straight from the 2 bags to 6 apples to double that 2 and double the 6. And then they had 4 for 12. Nice.
Right. So also they could have a problem like this. I've got, let's say 42 oranges and 7 bags. How many oranges go in each bag? The answer to this is also a rate, oranges per bag. And those are kind of 3rd grade numbers. For 4th and 5th, we'd up the ante a little bit, maybe include some decimals. And that actually makes me think of a problem string that you do a lot with 3.2 ounces per bottle with of eye drops or whatever, with a variety of numbers of bottles. We just don't, as 3-5 teachers, stress the rate part of it. We just solve the problems.
Yeah, but you absolutely are dealing with rate problems.
Absolutely.
So sometimes I hear the argument, we should not use ratio tables in 3rd, 4th, and 5th grade because students don't learn rates. And if you look at the Common Core state standards, or often a lot of the state standards don't have students really deal with rates until 6th grades. But we actually do a ton of problems in 3, 4, and 5 grades dealing with rates. We just, like you said, you don't stress the rate part of it. You just sort of solve the problems and off the kids go.
Right. So what about non-unit rates?
So non-unit rates is sort of the land of the middle school. That's where I've got problems where I start with something like, hey, I got a deal for you. You can get 4 slices of pizza for $5. And then you ask students to solve for different amounts of money for different numbers of slices of pizza. Or you might say, I'm in the bulk food aisle and I happen to put 2.4 pounds of flour in a bag and they charged me $1.20.
Mm-hmm.
And then you could ask questions about different amounts of pounds of flour and different amounts of money, and how much flour could you get for different amounts of money. You could also ask questions like, the ratio of the length of two sides of a triangle is 3:5. So then can you find the missing side length of a similar triangle if you know a corresponding side length? All of those are non-unit rate problems. And yes, we leave those non-unit rate problems for the middle school. We really let them dig into rates and the idea of unit and non-unit rates. We don't make a big deal of that in grades 3-5. But in grades 3, 4, and 5, we can use ratio tables to multiply and divide, actually as tools for helping kids think through multiplication and division problems.
Yeah, and not just single digit facts. It's not just a table of multiplication facts. It's a powerful model that we use to actually do problems, to compute. You want to give us an example?
Absolutely. So sure, I could have the multiples of 7. That
Yep.
could be one way to do that. But let's conceive of one pedagogical use of ratio tables.
Okay.
What if I were to give students a lot of different sort of starting numbers and ask them to find, say, 1 through 11 of that number? So I could say, hey, you've got 7s.
Mm-hmm.
Go and create 1 through 11 7s on that table. Go. And you've got 8s and you've got 9s. I might do 7s, 8s, and 9s because those are facts that students kind of they're harder for students. And so I might do those for some of the students that are kind of tripped up with those facts. But for other students in the class, I might say, you do 25s and you do 36s and you do 27s. Like I might give them some crazy numbers. And again, what they're doing is they're creating tables of 127, 227s, 327s, 4. So not a very interesting table until we line them up against each other. We got this idea from Investigations in Data, Number, and Space, where the kids made these different tables using different sort of rates. And they created, like I said, 1 through 11, 1 through 12 of them. And then we began to compare. We started asking questions like, hey, what do you guys notice? What are all the 2s? Oh, they're kind of double. What are all the 10s? Right. Wow, there's this 0 thing showing up everywhere. It gave us a chance to kind of talk about the times 10 thing as they start seeing what happens times 10 all over the place. And you might say, Pam, what if the kids like goof and they don't get, like 27, the 10 of those 27s is 270. Well, when most of the tables in the room have the 0 thing, then we could go, maybe we need to check out this table. Yeah. Like, sure enough, it should have been, like we can kind of like find that pattern and we can kind of use it. We can also ask questions like, can I go from the 2 and the 4? Like, is that always double? That's interesting. Hey, how's the 5 related to the 10? Mm-hmm. Oh, it's just half every time. That makes sense. So there's lots of different ways we can find patterns just looking at those tables. So that's a fine way to do it. But we can also use ratio tables. Guys, this is our favorite way, Kim, right?
Yep.
As a tool to solve problems.
Sure.
So picture a problem like, let's do a specific example. 42 times 15. Y'all, if you're driving right now, you might want to just turn it off for later. Or just do the best you can to picture stuff. And then maybe later, maybe write some stuff down on papers just to kind of keep track of what's going on. But if I was going to think about a problem like 42 times 15, could I conceive of that as 15 42s? 15 42s, right? Mm-hmm. So if I was going to think about it as 15 42s, my ratio table might look like this. I might say, well, I'm going to start with 142. So 1 to 42. And I'm going to think about, say I need 15 of them. So I'm going to think about 10 of them. That gets me pretty far, right? And that's an easy chunk to think about. So then my next entry in my table might be 10 to 420. Yeah. Because I'm thinking about 10 42s. So then I've got 10 42s is 420. Then I might think about, well, I need 15 of them. So I still need 5 of them. Ooh, 5 is half of 10. So the next entry in my table might be 5. Now, how am I going to find 5 42s? Well, if I've already got 10 42s being 420, then 5 42s would be half that. Is that 210? Kim, I'm doing this here. Is that right? 210? And so then I might add those together because now I've got 10 42s being 420, and I've got 5 being 210, and I might add those together to get 15 42s being 630. Yeah, because I've added those together. That's a way, thank you. That's a way of thinking about 42 times 15. But if I may offer, I might have a student think about 15 times 42 and not be thinking about 42s at all. They might be thinking about 15s.
Right.
So let's see, how could I think about 42 15s? Well, if I'm thinking about 15s, that first entry in my ratio table could be 1 to 15, but I need 42 of them. So I think a first move I might make is two of them. You're like, two of them? Are you crazy? Well, watch where I go with that. So if I've got two 15s, my next entry is 2 to 30, right? That's two 15s. But I need 42 of them. So I need 40 of them. Ooh, I wonder if I could get four from there. So then I might say, what's 4 15s? So 4 15s, that's going to be 60. So far I've got 1 to 15, 2 to 30, 4 to 60. Bam! Now I can jump right to the 40 because now I can scale times 10. Once I have that 4 to 60, now I can think of 40 to 600 because I'm doing that nice times 10 thing. Well, remember, now if you're doing this in the air, hang on tight because I already had the two 15s is 30. And now I have 40 15s is 600. I just add those together. And now I have 42 15s is that 630, which is 630.
Right.
Whew. Okay, so that might be kind of hard for you to hang into the air. But part of our point is it's so easy to read off of a ratio table. Those relationships just jump out so clearly. It's so the facility to do that is so easy for students to sort of keep track of the nice chunks that they're using if they're kind of thinking in these multiplicative relationships. All right. We mentioned earlier that we can use ratio tables for multiplication and division. So Kim, I'm going to give you the
Awesome.
division problem. You're welcome.
Okay. Thanks for that.
Yeah. All right. So what about 192 divided by 6? Now, if you're listening to the podcast, y'all pause, solve that problem on your own a little bit. Well, how were you thinking about 192 divided by 6? Because that will help you sort of think about the relationships as Kim kind of tells you what she's thinking about.
Sure.
So then come on back. All right, Kim.
Okay, so I want
divided
a
by
pencil,
6.
but I'm not sitting near one, so I'm gonna try to picture in my head what I wish I had a pencil and paper, right? Because I'm drawing a ratio table in my mind. Okay, so you said 192 divided by 6. So immediately I'm thinking that means to me right now, how many sixes are there in 192?
Mm-hmm.
And so I'm thinking my ratio table is going to look like 1 to 6. So I'm going to start with, what am I talking about? I'm talking about sixes. So 1 to 6. And I'm thinking that I'm going to go 10 sixes is 60. And I'm going to 192. So I've got 1 to 6, 10 sixes is 60. So 20 6 is 120. Oh, actually, scratch that. Can I take that back? I'm gonna go from 10 sixes is 60, and then I'm gonna scale up times 3,
Okay.
and I'm gonna say 30 sixes is 180. And at this point, I think I'm gonna ask myself, how far away am I from my goal? So I'm at 180, and I know that I'm only 12 away from 192, and so I'm gonna write down 2 sixes is 12. And so then on my ratio table in my mind, I would have 1 to 6, and then 10 to 60, 30 sixes is 180, 2 sixes is 12. And I'm just going to use the pieces that I actually need, which is 30 sixes is 180, and 2 more sixes is 12. And that makes 32 sixes to make 192.
And so the last entry in your table would be 32 to 90 to 192.
Yeah.
Nice.
And
nice.
I don't think you mentioned this, but I think it's worth noting that we can put entries in our ratio table when it's a tool for us that we don't actually use at the very end to piece together for our final product or our final quotient, right?
Mm-hmm. Yeah, that's a really good point. So there's values that we might use. For example, in my ratio table, when I was thinking about 42 15s, I found 2 15s was 30. So I had the ratio 1 to 15, 2 to 30, 4 to 60, 40 to 600. And then I only used the 40 and the 2. I didn't use the 4. The 4 was just sort of in there because it helped me to get to the 40.
Right.
So yeah, ratio tables are so handy because I could put a lot of different things in the ratio table to help me get where I need to go. And then I could just use the ones that I actually need to finish solving the problem. Very
Yeah.
cool.
Yeah.
Hey, let me take that 192 divided by 6 and do one other really cool thing with a ratio table. Because we can conceive of division two ways. And you just conceived of division quotatively because you
Mhm.
thought about how many sixes are in 192. But we can also think partitively about that. And we could think about 192 divided by 6 as 192 to 6, or the division, like if I were to write it as a fraction. So 192 sort of with that division line kind of over the 6. And that's just so you kind of picture it in your minds. It's not a mathematical relationship, but 192, the fraction 192 sixths. And then I can actually use a ratio table to simplify that ratio. It's the ratio of 192 to 6, and I can simplify it. I might think about, well, I can cut both of those in half. So if I cut 192 in half, that's 96. And if I cut 6 in half, that's 3. So now I have two equivalent ratios. I've got 192 to 6 is equivalent to 96 to 3. And then I can think about, what is 96 divided by 3? Well, 90 divided by 3 is 30, and 6 divided by 3 is 2. So that's 32. And we get the same. So the 192 divided by 6 is 32. Two different ways that I can use a ratio table, two different ways we can conceive of that division problem, but both using this powerful tool as a ratio table to help us kind of think through the relationships that we're using. Woo! So y'all, give me a multiplication or a division problem, and I'm going to use a ratio table as the tool to solve it. So to be really clear, I don't know that we've said that yet on the podcast today. Neither Kim or I use kind of that traditional multiplication where you line them up and the magic zero and all that stuff, nor do we use the long division algorithm where you do the house top and I don't even know all those things, kids, brother, sister, mother, father, and the does McDonald's sell cheeseburger. Wow, all those crazy, something about monkey smelling bad. There's all these crazy rhymes that teachers have made up, rhymes or mnemonics that teachers have made up, stories to help kids remember the steps of a long division algorithm, because the long division algorithm is so hard to understand that nobody even tries to understand it. They just try to memorize the steps by using all these crazy things to memorize it. Or could we help kids think and use relationships by using a ratio table as that tool to help them keep track of their thinking? I know there's the lucky 7 out there that people use to represent partial quotients. We would recommend instead ratio tables. Ratio tables don't force kids into crazy subtraction where they are sort of nudged into using the subtraction algorithm. Instead, they can still be thinking and reasoning, using what they know, using the relationships they understand to solve those problems. All right, so if some of what we did today was a little hard to picture, totally get it. We've got a download for you that we are going to we're going to listen to this, and we're going to keep track of what we did, and we'll put it on paper, and then you could re-listen to this podcast and kind of see what we meant as we were kind of using, what does a ratio table even look like?
Yeah.
But we'll give you some examples on that. So check out the show notes to download that. And we'll totally give you that link where you can look at what ratio tables actually look like, because we know we were doing that in the air.
Perfect. If you want to know more about this amazing tool that we love so much, we would love to invite you to check out the Facebook Lives and webinar that Pam's going to be hosting later this month. And if you're listening to this after those, you can check out her YouTube channel, Figuring Math, and find those lives and webinar.
Yeah, we're going to be doing 4 Facebook Lives and a webinar that we'll repeat. You're going to want to register for that webinar and check out the Facebook Lives. It's going to be a lot of fun where we're going to really get down and dirty and lots of examples for this super cool tool we call a ratio table. Remember to join us on Math Strat Chat on Facebook, Twitter, and Instagram on Wednesday eves, where we explore problems with the world, and you will see ratio tables solving multiplication, division, and proportional reasoning problems. So, if you're interested to learn more math and you want to help your students develop as mathematicians, then don't miss the Math is Figureoutable podcast, because math is figureoutable.